Good morning, everybody. If we can start with some green check marks, please, and we'll get going in a second. Hopefully everyone's doing well today. Thank you. Few things. It is obviously Thursday today. The sort of mark cutoff for our interim reports will be tomorrow at, I want to say 3. Yeah, let's make it tomorrow at 3. I believe that's what we put in the course there. So if you do want to get work submitted and get an accurate grade at this point in the term, you need to have all your work done for tomorrow afternoon. And what have we done, sort of thing. So what will be included on that report will be units 1, 2, and 3, just the biology stuff. We've started into unit 10 last class, but the unit 10 material won't be on there. So we're looking at units 1, 2, and 3. With units 1, we had a create a creature assignment, unit 1 had a chromatograph, unit 2 had a create a creature, and unit 3 had a nutrient cycles paragraph talking about how a nutrient gets cycled through the atmosphere or through its cycle. So essentially you have those 3 assignments, 3 learning guides, 3 reviews, and 3 tests. And the unit 3, the unit 3 test is quite short. I think it's only 12 or 15 questions. So that's kind of where we're at in terms of the interim reports. That's what it's going to cover. I had asked that you guys would have submitted your unit 3 work on Tuesday's class. So that should have given you an opportunity to submit that. I will mark it, send that password out to your guardians or parents, and then you would have had an opportunity to write that test hopefully by now. In a perfect world, we know we're not in a perfect world, so sometimes we are at different places, and that's okay, but we can't get too far behind, so we have to have some deadlines and whatnot. So moving forward, for sure we're going to finish unit 10 before the break, March break. Obviously next week is the last week of class before we're off for 2 weeks. So you guys will need to finish units 1, 2, 3, and 10 before March break. And we'll actually probably finish up unit 10 on Tuesday's class. And then I'm not sure what Thursday's class is going to look like yet, but I want everyone to be done for units 1, 2, 3, and 10 prior to March break. I don't want you guys to have to do any work over the break. I think it should be a break. So if you've managed to kind of keep pace with where we're at, then you should be good, and we'll start fresh in unit 4 after the break. Madison, just saw your question here. When is the midterm? We haven't picked a firm date for the midterm yet. We'll do that next week sometime. It'll likely be around the end of the first, or I guess it's technically the 3rd term, so the first half of this semester, usually about the middle of April sometime. I haven't picked a date. There's a lot of things. We have to arrange a room and, getting people moved in and out, and we have to pick a day that works for everyone else. So I promise you I'll have that date out to you by next week, by the end of the week. And the midterm will generally cover units 1, 2, 3, so the biology stuff. It'll cover unit 10, which we just looked at. And then when we get into unit 4, it's the chemistry material. It's a lot of material, so we kind of break all the units down and spend a lot more time on each of the kind of sections in units 4 and 5. So sometimes we'll get a little bit of the chemistry in there as well, just the beginning stuff. So I'll let you know exactly when it is, and once we get through March break and start class again, I'll give you a couple weeks notice and let you know exactly what's going to be on it in terms of material. So hopefully that sorts things out. There's a few of you without green checks came in maybe a little bit late or haven't yet woken up. I'm not sure what the case may be. You want to throw in some green checks? Did anybody have any questions regarding section 10.1 in the learning guide? There was some, there's always questions at the end of each section. Just kind of practice and make sure you guys are looking at the work and whatnot. Did anybody run into any problems there? I could bring it up. I believe I have it here. Oh, I don't have a cursor. That's a problem. Oh, there it is. All right, so Unit 10 Learning Guide. You guys have been through this. Evidence for continental drift. These questions on page 4 and 5. Did anybody run into any issues here? Again, I don't love the fact that they expect you to know who Alfred Wegener was and what he did, but unfortunately that's kind of the reality of it. So you need to know Wegener, you need to know his evidence. So Wegener had the continents fitting, he had the mountain ranges extending across continents, and he had the fossil evidence and ancient glaciers. Those were kind of his big pieces of his theory of Pangaea. And he couldn't explain why. That was kind of his problem. So nobody has any questions there. We'll move on. We're going to get into 10.2, which is, I don't know, I think it's pretty interesting stuff, but I'm just a silly science teacher, so what do I know? Talking about plate tectonics, which in terms of earth science and geology, geography, is kind of like the coolest stuff there is. Because things that happen, like when you look at, if you're a geologist, you're going to go look at a rock. And you're going to look at the rock and be like, this is a rock. It's old. That's it. It's just a rock, really. That's kind of boring. But when we start talking about plate tectonics, we're talking about things like earthquakes and volcanoes and boundaries and really interesting stuff. In terms of geology or earth science, things happen on very, very, very large time scales. So we're talking thousands, hundreds of thousands, millions, hundreds of millions, and even billions of years. Very long time frames, kind of nothing really happens quickly in this sort of world. But when we start talking about plate tectonics, we can see things happening in our human time scale. Talking about things like earthquakes and volcanoes, you can go check these things out. Very exciting. So, first thing we need to do is cover off the layers of the Earth. And Earth's about 1,200 kilometers thick from the surface to the center. And there's some layers. The upper layer is the crust. It's very thin. Some places it's very, very thin, like 5 kilometers thin, averaging, around 50 to 100 kilometers thick, depending on where you're looking. So that's the crust. That's the outer layer. That's the stuff we stand on. That's the hard stuff, rock. Then we have the upper mantle and the lower mantle. So we break the mantle into 2 parts. And we talk about the mantle being able to flow like thick toothpaste. So this lower mantle, find my cursor here, the lower mantle, this kind of reddish section here, it's kind of like a solid, but it's really, really hot solid, and it kind of flows like a toothpaste would. Kind of like, really, really thick lava, if you've ever seen some videos of lava or seen it in real life. The outer core, we think the outer core is made of, it's liquid. We're not entirely sure. And then we have the inner core, which is a solid. And because it's, so far down there, it's absolutely immense pressure. So we do know for a fact that the outer and inner core are both solid and liquid. And we'll talk about why we know that now. We're not entirely sure what's going on in the that mantle, the outer mantle and inner mantle. We don't have a lot of information about those layers. So when you are assessed on this sort of stuff, do you need to know how thick each of the layers are? No, you don't have to say the upper mantle is 660 kilometers thick on average. You don't have to know that. If you knew the 5 layers, like inner core, outer core, lower mantle, upper mantle, and crust, and where they are, that would be awesome. That'll get you through like 99% of the questions related to the layers. So again, you don't have to memorize the thicknesses of each layer, but you should know what each layer is called, be able to identify it. All right, so if we look at the image here, Crust is about 5 kilometers. The upper mantle is 660, lower mantle's about 2,000 kilometers. The outer core is about 2,000 kilometers, and then we have the inner core is about 1,000 kilometers. So in all, I've got Earth is over 1,200 kilometers thick. It should be 12,000 kilometers thick. So how deep have we been? When we talk about like humans, on the human scale, how far have we gone down into the Earth? We know what's down there. We have a pretty good idea about what's down there. You know, how far have we been? Anyone want to take a guess in terms of kilometers, how many kilometers we've gone down? We drill holes for like oil refinery and mines. We drill holes and go down, check things out. There's actually been studies just to see how far we can go. There's no sort of limits, obviously, to what we can deal with. But any ideas? The furthest we've gone into the Earth. Lower mantle and or outer core, okay? Anyone else want to take a guess? Or is Kyla the only brave soul in class today? Or the only awake person? Leads? Leads, if you say something like we've dug down until we found a unicorn, no, I'm just kidding, Leads. All the way to China. I was reading something the other day. It was kind of interesting. Maybe, I don't know. It said if you drilled a hole right through Earth all the way to the other side, it would take, and you jumped in, it would take 42 minutes to go all the way through and pop out on the other side. I thought that was interesting. Jesse's got a 5 kilometer guess. So we've got lower mantle, 5 kilometers, and not past the crust. That's a pretty good span of guesses. Here's an image. I apologize that it's in imperial units, but we've converted imperial to metric in math, so you guys are experts at this. So this is an image of, you know, the deepest we've ever been. So in France, the deepest natural cave is 5,000 feet, which isn't really that far, a mile and a bit, or a couple kilometers. The deepest mine, so this is literally the deepest any human has ever been. It's in South Africa. I believe it's a diamond mine, 12,000 feet, which is, you know, about 5-6 kilometers. And then offshore drilling, so in the seabed, we'll talk about why this is significant in a second, is 5,000 feet, so that's in the ocean floor. There's a well, an oil well. They found an oil deposit about 6 miles down in Oklahoma. So they dug about 6 miles down to hit that oil deposit. And then in Russia, or the Soviet Union, when they actually dug it, there's the Kola well. And they went down 7.6 miles. Really, well, I find it interesting. Interesting story about the well in USSR, Soviet Union. They'd intended to go deeper. They had a goal of, I think, 12 miles, but they couldn't quite get down there. So there's some issues there. Josh, wasn't there a borehole that caused an earthquake? Are you maybe referring to some of the stuff related to fracking, Josh, or were you specifically talking about a borehole? Because there is a lot of evidence that suggests that it was a borehole. Yeah, I'm not sure. It's entirely possible. I'm not familiar with it, Josh. So fracking is where you dig a hole down into the ground and then you push fluids through the hole, and it kind of pushes the oil out of the ground, and you break all the layers up so the oil can kind of flow out. And they've actually proven that there's a correlation between fracking, inserting high pressure liquid into the ground to break the layers, is actually causing earthquakes. So we'll look at some earthquake stuff here in a second. It's possible, Josh. I'm unfamiliar with it, so I won't probably comment on it. So anyways, the crust we talked about being about 5 kilometers thick at its thinnest point and about 70 kilometers thick at its thickest point, and we've literally gone down 7 miles. So, we'll call it, 12 kilometers. This is as far as we've gone. So We haven't even made it halfway through the crust. Earth's big, first of all. Why can't we go any deeper? What's the problem? Why couldn't the USSR, this borehole, to see how deep we go, why were they limited to 7.6 kilometers? Why could they not go any further than that? Same out in the ocean. Bedrock would be a really, really great guess. But we are very good at drilling through very, very hard things. We got like dynamite, we can drill down through the hardest rock. So it has a little bit to do with rock type. We pick areas with soft rock for sure, but it wasn't the actual consistency or the density of the rock. We can drill through bedrock with like diamond tipped drill bits and all sorts of stuff. Any other guesses as to why we can't go any deeper than 7.6? And again, this is like a tube, this big. When I say like we've drilled down that far, it's not a human that's gone that far. It's just a hole that's that deep. The lowest a human's ever been is in South Africa in this mine, about 12,000 feet down, or a kilometer and a bit. So we're not sending people down. We are just drilling a hole this big, pretend. I don't know exactly how big it was. Drilling a hole this big just to see how far we can go. Just send a drill bit down there and just see how far we can go. Yeah, the equipment is the problem. And Josh, you actually got what I was trying to get at. It's actually so hot down there that the drill bits start to melt. And the crust isn't very thick in some spots, and it is thicker in others, but even though we're only down like a couple kilometers, let's say 12 kilometers down, it's so hot once you get down that far that it can literally melt the metal. There's just immense pressure from all that rock under there kind of being forced down, gravity causing all this stuff. So yeah, it's actually the temperature that we run into that is a bit of a problem, because it gets very, very hot once we get down that far. So that's as far as we've gone. And it's usually about this point, then somebody says, Mr. Borden, you said we know what the layers of the earth look like, yet we've only been down. Let's look at a scale cross-section again of the earth. So here's the crust on this. My cursor keeps disappearing. It's devastating. We have the crust. The crust is this tiny little layer, and literally you can see it just like a thin line. And the crust is only 5 kilometers thick in some spots, 70 in others. We've only been down, 10 kilometers. So we've literally kind of scratched the surface. How do we know that the upper mantle is the upper mantle and what it's made of, and the lower mantle and the outer and inner core that are solid and liquid, if we've never been there? How do we know? My goodness, it's so confusing. And we'll actually talk about it later today. Josh, you're right, steel melts at 10 degrees Celsius. So there's a couple things going on here. When we send a drill down, not only is it existing down there, but it's rotating and drilling. So there's even at the surface, if we were to drill into rock, it would get extremely hot just because of the friction and energy sort of involved with a drill bit there. So that was kind of, there's sort of two things. Being deep into the earth, it's very hot, and then having a drill bit spinning at that really, really low depth adds a lot more heat to it. So they start melting as a combination of the Earth's heat plus the actual heat of the drill. So we can't go any deeper with the current technology that we have. This USSR well was 67 years ago. That's the deepest we've tried to get. We probably have technology that could allow us to go deeper now, but there's not a lot of, there's some incentive to go farther, but not a ton. All right, so obviously these tectonic plates we're going to talk about. The tectonic plates are kind of on the top on the Earth's crust, and they kind of float around on that mantle. And that mantle is kind of really thick in consistency, like toothpaste. So when we talk about it being liquid, it's not a liquid like a water liquid. It's like a liquid like a, I don't know, it's hard to describe. A really thick liquid. It's literally molten rock. So as if it wasn't confusing enough to give you the crust, the upper mantle, the lower mantle, the outer core, the inner core, the 5 layers, we've decided, hey, let's really confuse students and come up with 2 additional words that don't actually comprise a full layer. So to add to the confusion, we come up with 2 additional words, the lithosphere, which is the crust, plus the top part of the upper mantle, and the asthenosphere, which is like the bottom part of the upper mantle. The reason we have this distinction between lithosphere and asthenosphere is that the lithosphere is kind of the hard stuff that kind of floats on top. So we have the crust, which is varying in thickness, and then just below the crust, the very, very top part of the upper mantle, about 70 or so kilometers of the upper mantle, is also very solid, and we call that the lithosphere. And the lithosphere is quite literally floating on the asthenosphere, which is kind of the liquidy toothpaste part of the upper mantle. I'm going to see if I can find my cursor again. It's really interesting that we got this new laptop for the studio, which was very exciting. It's brand new. It's a Lenovo Yoga, stylus, everything you could hope for. Fast. Another colleague here has a pretty amazing Lenovo Yoga, just like mine, and we tried to use it yesterday to connect with a virtual field trip down in Florida, or no, in Texas, pardon me, and it literally didn't work. And now I have this computer, and you guys have, been with me experiencing how bad it is for a brand new computer. All right, let's try this again. I appear to have a cursor now. All right, so there's kind of 2 types of crust. You have oceanic crust, which is very thin, and then continental crust, which is very thick, which kind of makes sense. So imagine the Earth had no crust at all. Imagine the Earth was just it was perfectly smooth all the way around, and then we covered it in a thin layer of water. So that's Earth. Perfectly smooth sphere, a thin layer of water on top. Perfect. That would be kind of like a perfect world scenario. Now if we took something really thick, like a continent, and dropped it into the ocean, the ocean would kind of form around the continent. So because that continental crust is so thick, the ocean can't cover it. It sticks out of the ocean. So when we talk about there being kind of 2 types of crust, the oceanic crust is covered in water because it's very thin, and then we have the continental crust, which is very thick, and it's not underwater because it's so thick. So the asthenosphere, we talk about being semi-liquid. It's not like a liquid like water like we think of it. And then the one really important point on this page is that the heat which the asthenosphere keeps it melted. So this asthenosphere is this liquidy bit here. The heat that keeps this melted it comes from 2 things. The big one is radioactive elements. So there's radioactive uranium and all sorts of other elements in this asthenosphere that are decaying constantly, and they cause a lot of heat, and that keeps this layer liquid-ish. And there's additional heat from the formation of our planet, which is relatively young. Sort of the pressures of planet formation is also still contained within this layer as well. But the big one is radioactive materials, is kind of what keeps that layer liquid. Okay, we had this idea that that Wagner came up with, puzzle pieces, Pangea, things are starting to move. He didn't come up with why they were moving until later. There was a couple other gentlemen, Hess and, forgotten the other guy's name, Wilson and Hess. They came up with some theories as to why things were moving. So imagine the Earth is a bunch of these plates, and they're kind of literally like plates. They're not round, but they're plates. And we said, okay, there's convection currents going in that asthenosphere that cause the plates to move. We know the plates have moved. We can see it in the Mid-Atlantic Ridge. We can see the plates moving on land. We can actually see fault lines, and we can see the plates physically moving. They go very slowly, but we can see them moving. So this is the idea as to why the plates are moving. This is called ridge push. So you get a strong convection current. Of course, my cursor has disappeared again. So you get a strong convection current, so hot magma, less dense, rising, same idea as a hot air balloon. Why does a hot air balloon float? Because the air is hot in it, it's less dense, hot things rise. Magma, underneath in the asthenosphere, pushing up under the crust. Well, eventually the crust is going to break because we have all of this magma pushing up. So it's going to break and it's going to get pushed apart, and new magma is actually going to fill in the gap, which is fairly interesting. So if you can imagine these huge plates of continent, Pangaea, and we have this really, really strong upward force of magma, and it starts to push the plates apart. And as the plates start to break apart, you get magma flowing through, volcanoes are formed, things like that. Magma starts making its way through. Well, these plates start to get pushed apart further and further, and you get what's called a rift valley. And that valley will eventually get thin enough that some water will either collect there in terms of a lake, or if it's close to an existing ocean, water will start to fill in that rift valley, and you'll get an ocean. And then you get this further and further convection occurring, and eventually you end up with something like the Atlantic Ocean over millions of years. And in the middle you have the Rift Valley, which is indicated, which will eventually turn into an oceanic ridge once it gets covered in ocean water. So this is kind of what causes these plates to move. Now imagine a plate, imagine this being a plate. Now on this side I have magma rising up and it's pushing the plate over. Well, if you have a plate and it's pushing the plate over, if it starts to get pushed, something's going to happen on this other side. It's not like the plate can just keep going that way. It's bumping into something, and the plates are all touching on every side. So we run into some interesting things where the plates start to meet up. So here's kind of the complete picture, all in one diagram. Oh, cursor, yes. All right, so we get a really strong convection current rising up. Oh, this is devastating. And that convection current rising up causes that plate to get pushed. You get ridge push. Well, what happens at the other end? Well, at the other end, that plate is bumping into really, really thick continental crust. So instead of going kind of like over top of the thick continental crust, because this oceanic crust is so thin, it gets pushed under the continental crust. So what happens is we get something called slab pull. So these are the two things in combination that cause these plates to move. You get a large convection current, which starts to push this plate. The plate says, oh no, I have nowhere to go. And on the opposite end, it has to dive under this thicker plate. And once it gets really, really deep down here, it gets very hot, and this rock that was once oceanic crust, it starts to heat up, heat up, heat up, heat up, and as it gets further and further down, it melts, and it just continues this cycle again and again and again. So you have a continuous cycle. So you have two plates coming together over here, you have two plates being pushed apart over here, and that is what is happening to all of the plates on Earth. Somewhere, somehow, you have magma rising up, the plate gets pushed one way, it bumps into something, it either has an opportunity to go under or kind of run into something else. Maybe the other thing goes under it. That's what's happening on all of the plates. So Where we have these two plates coming together, we call it a subduction zone, and that is the most common place you'll find an earthquake or a volcano, which is pretty cool. So ridge push, slab pull are kind of the two big vocab words here. Slab pull is once it starts to get pulled under, it's like a tablecloth. If you ever set the table, you put a tablecloth out, and if it's not completely centered, it starts to go over the edge. Once it starts going, it just gets sucked right off the edge. Once all of that gravity starts pulling it off the edge, that's exactly what's happening to these plates at a very slow scale. It's kind of like a tablecloth. Once it starts to fall over the edge, it just keeps going. So this is a kind of a simple look at all of the plates of the Earth. Obviously, we've taken a sphere and turned it into a rectangle, so the scale on the corners is a bit off, but it gives you a bit of an idea. There are smaller plates, but these are the major ones. So there are many, many other plates that exist, but these are the big guys. And in your data booklet, your learning guide, not your learning guide, in your data booklet, you actually have an image that's very similar to this. That shows all of the plates. So the Pacific Plate is kind of our neck of the woods. So we have the Pacific Plate, big yellow guy here. We live on the North American Plate. And just off of our coast, we have this Juan de Fuca Plate, which is just a little tiny plate. Cocos Plate down towards Central America. And then we have some other plates. The interesting one is the Australia Plate's kind of oddly shaped, kind of going all the way from New Zealand over to Australia. That's a bit of a strange one down here. It has a really odd shape. The Nazca Plate in front of South America. Antarctic Plate looks really big across the bottom, but of course we've taken the bottom of a sphere and kind of stretched it out, so it's not really that big, the Antarctic Plate. The Scotia Plate's an interesting one, kind of just hangs out in the middle of the South Atlantic. And we talked a little bit about the Mid-Atlantic Ridge last day, and this you can see it really well. We have all this fresh lava, magma coming through here down the middle of the Atlantic Ocean, where these two continents used to touch. So when we look at the plates, you can see how the plate would fit really well. Sort of this African plate and this South American plate fit together so well. And then the Eurasian Plate. India is kind of its own little fun plate here in the middle. Saudi Arabia, India both have their own plates. So those are kind of the big plates. And again, they're broken into much smaller ones eventually, but on a big scale, those are the big guys. So this is the picture that you guys get in your data book. This is the exact image taken out of page 7 of your data book. If you do have a data book printed off, we're going to look at them here for the next little while, so you might want to go find it, grab it, if you have it kicking around somewhere. Again, this shows all the plates, but it doesn't have the pretty colors that the last picture had. One interesting thing on this is it shows you where mountain ranges are and where volcanoes are, and shows you all the different types of plates, types of plate boundaries. One interesting thing about where we live, maybe even closer to the coast of like Vancouver up the coast towards Alaska, is that if we look at this diagram, we can see that there's a bunch of volcanoes right off our coast. You can see Vancouver Island, and right next to Vancouver Island there's a volcano. So volcanoes are indicated here even though they may be dormant. So believe it or not, British Columbia is a pretty volcanically active in terms of volcanoes, but most of the volcanoes are kind of taking a bit of a nap for now. So we'll look at volcanoes here later today. So that's the page right out of your data book. There's an additional page that has just the British Columbia, northern United States up to Alaska, just looking at our sort of area, so we can be more specific to what's going on right off of our coast. So we have some really interesting things happening at off the coast of BC here. We have the Juan de Fuca plate, which is actually getting pushed under the North America plate. So there's this little tiny plate, and it's actually getting pushed under, which causes all these volcanoes through BC and down into Washington State. There's two smaller plates, the Explorer plate, and just below that's the what's it called? Gorda plate. I always forget the Gorda plate. So that's our area. The diagrams are important, the arrows are important, the legend's important, so we'll talk a bit about that. So a plate boundary is where two plates are in contact, and the way they interact is based on the direction the plates are moving and how thick they are. So we have three options, and we'll kind of lump all of the interactions into these three categories, and then the three categories can take place either with two continental plates, two oceanic plates, an oceanic and a continental. So there's kind of subcategories, but two plates can run into each other. That's one option. Two plates can be pushed apart from one another. That's another option. And two plates can slide past one another going kind of opposite directions. That's a third option. Those are the only three things that can happen. Now again, we'll kind of talk about subcategories of these things, but they're either coming together, they're either being pushed apart, or they're either sliding past one another. Those are the three things that can happen. Come together, pushed apart, sliding past. That's it. We call them convergent. If they're coming together, that's converging. Divergent is moving apart. And transform boundaries are sliding past one another. So let's look at some divergent boundaries. So these are areas where plates are getting pushed apart. We have a strong convection current in the asthenosphere, the upper mantle, pushing up. It eventually will start breaking through the surface. And as it starts to break through, because it's pushing up so hard, the plates actually kind of get pushed apart really slowly. Now, if this happens under a continent, you start with a rift valley, so a valley will form. What happens to valleys? They get filled with water. We live in the Okanagan Lake. It's at the bottom of a valley. The valley is filled with water because it's A, low-lying, and B, used to be covered in a large glacier, left some water behind. And then eventually, if the Rift Valley continues to grow, it'll fill with water fully. It'll become an ocean, and then as time progresses, it'll get further and further apart, and you get a bigger and bigger and bigger ocean. Again, these things, like these three images, would be over millions of years. We're not talking really quick or short time frames, very, very long periods of time. So that's a divergent plate boundary. Now, if you have your data book out, hopefully you do somewhere, see if you can find a divergent plate boundary. So I'll go back to the map of the world. Divergent boundaries are indicated on the legend with these kind of two lines next to each other. So at the bottom you can see here it says divergent boundary. And you're just trying to find examples of divergent boundaries. So just in chat, throw in the name of a divergent boundary. Costin, I'm not saying Okanagan Lake will be an ocean. What I'm saying is that low-lying areas fill with water. Because of our location, we're kind of off the coast of Fairways. We have that plate off of Vancouver Island getting kind of pushed under. We're so far away from that you know, our area isn't ever really going to fill in with water because we're really thick. We're about a kilometer, or I guess we're 300-ish meters above sea level. So because the plate's so thick under us, we don't have a divergent boundary under the middle of Okanagan Lake. We're not going to end up with an ocean here. Be interesting if we were. Yeah, Madison. We'll talk about earthquakes in a second. But yeah, they're The Vancouver area is due for a large earthquake. Typically you get one every, a few thousand years, and we haven't seen one in a long time. So we'll talk about why that is in a second. We've had a few earthquakes off the coast of BC recently, very sort of minor ones, which is kind of considered a good thing. As long as you have a bunch of minor ones, you don't end up with a big one. Well, there's no guarantees, but there you go. So we'll talk about earthquakes in a second. I'm going to challenge you, since nobody is putting in a divergent plate boundary, I challenge you to find a divergent plate boundary on a continent. So in the map behind me, somewhere on Earth, there is a divergent plate boundary on a continent. It's not in the middle of an ocean. So we've talked about the mid-Atlantic ridge, that's a divergent boundary. Where is the only sort of obvious divergent boundary on a continent? So we're going to look at it really closely here in a second. Yeah, Eric, you got it. Right in the middle of Africa, or kind of on the east coast of Africa, there is actually a split. So there's a convection current under the African plate. Kind of see it right here. So actually Africa is, in a few, not even a million years, but a few thousand years, this is actually going to be an ocean right through the middle of Africa. It's actually starting to form already. Obviously in our time that we're here on Earth, we'll never see it form because it takes so long, but eventually there'll be an ocean through the middle of Africa, right down through here. And if we look at some images of Africa from space, we'll see what would you expect to find here right now? Well, you'd expect to find low-lying areas. And if we do look at an actual picture from space, there's a bunch of lakes and whatnot there right now, because as those plates split apart, the crust gets thinner and thinner and thinner, and water starts to fill it up, and you end up with lakes. Those lakes eventually will turn into an ocean in a while. A couple million years, no big deal. All right, so that's divergent boundaries. On the map, divergent boundaries are those two lines next to each other, and that indicates that those plates are being split apart. So here is a picture of the divergent plate boundary in Africa. This is actually a picture from a plane in Africa. You can see very clearly, the picture that's beside me here, the actual split in the plate. So you can see this kind of white here, and then another kind of cliff over here. So this is an actual rift valley being created in Africa. The two plates on either side are kind of being pushed apart, and because it's underneath land, you get these kind of volcano spotting along the way. So pretty amazing that we can actually kind of see this in real time. So what does it look like from underneath? If we took kind of a cross section, we have this huge rising plume, also known as a convection current, pushing up underneath this African plate. For whatever reason, there's a convection current under the edge of Africa right now, and we're getting this African Rift Valley being formed, and it's slowly being filled in with water. So if we look at kind of a hand-drawn picture down below here, you can see that the current situation there where these divergent plates are, it's starting to fill in with water. So I believe it's I don't even guess the name of the lake. I believe it's Lake Titicaca is the biggest lake in Africa. I think that's the one that's there, and that's starting to fill in that Rift Valley. Eventually, part of Africa is just going to be kind of broken off because it's on a different plate, the Somali African plate. So there you go. That's happening right now as we speak in Africa, a divergent plate boundary on land. So the other option, instead of plates being pushed apart, is plates coming together. And we kind of run into three scenarios when we talk about plates coming together. We can have two oceanic plates coming together. We can have oceanic and continental plates coming together. And let's just start with oceanic continental convergence. So you get a really thick continental plate, kind of light and fluffy, and you get a really thin, very, very, very dense oceanic plate, and they're getting pushed together. And because this oceanic plate's so thin compared to this really, really thick continental plate, it has no choice but to be pushed underneath. As it gets pushed under, we get immense friction. Imagine, like, quite literally millions and millions of tons of rock being slid past one another very slowly. You get very, very large amounts of friction, lots of heat produced, and this rock here starts to melt. And as it melts, it kind of works its way through the crust because this really less dense magma pushes its way through, and you get a volcano happening right above it. So the volcano, notice it doesn't happen where the two plates are meeting. It doesn't happen at the trench. So where the two plates meet, you get a really deep trench. The volcano actually happens inland a little bit because of all of that magma rising up because of the frictions actually. It doesn't get hot enough right here where they just meet. It takes a while for the heat to be produced, and then it rises up. So we're going to look at a bunch of examples of this here in a second. So the oceanic plate is really dense. It subducts, which is another sort of vocab word. It actually gets pushed under the continental plate. You usually get a trench where the two plates kind of meet. And just a little further inland, typically you'll end up with a bunch of volcanoes, and especially cone-shaped volcanoes. And these are the volcanoes that we see in our area. So the coast mountains are actually a result of this because the two plates are getting pushed together. If you've ever been to Vancouver, you look off kind of to the east and you see all of the big mountains that kind of go behind Vancouver. Those are all a result of that Juan de Fuca plate being pushed in to the Pacific plate. Because it's being pushed, the plates kind of get crunched up and they start to, get pushed up. All right, so in your data book, hopefully you have one out right now, I want you to find an example of an oceanic continental convergence. So you want to find an oceanic plate running into a continental plate. And if you're like really savvy in geology or geography, you could maybe name the mountain range that's produced. That would be, really cool. I'll go back a few slides. We'll look at the pictures just in case you don't have your data book out. So we're looking for a converging plate boundary, and the converging plate boundaries have this line with the triangle down here at the bottom. So convergent boundary looks like these kind of dotty, triangle-y deals. So we're looking for a convergent boundary between an oceanic plate and a continental plate. Can anyone name one? Find one somewhere, anywhere. Any ideas? Any ideas? An oceanic plate and a continental plate coming together. This isn't going to go well on the test if we can't find it in class. All right, let's look off the, we have the Pacific plate right here. If I can get a cursor to appear. There we go. This Pacific plate is getting pushed under this big Eurasian plate. And as a result, we get some islands being formed, places like Japan. This is also happening on the kind of other end of the world, right off our doorstep. We do have a little bit of it happening with the Juan de Fuca plate, as I mentioned, being pushed under the North America plate. So you can see the symbol here, the convergent plate boundary along there. And the best example is down in South America. So we have the Nazca plate, which is almost perfectly being pushed under the South American plate right at the coast. And as a result, we get a very, very active chain of volcanoes through Chile. And we get a mountain range formed called, does anybody know the mountain range off the west coast of South America through Chile? Somebody surely knows what these mountains are called. Very young mountain range. Those are the Andes Mountains. All right. So the first type of convergent boundary we talked about is oceanic plate coming in and hitting a continental plate. Because that continental plate's so thick, the oceanic plate goes underneath it. As it gets under, all that pressure pushing it makes the mountains bigger, and then we get volcanoes being formed as well. The second type of convergent plate boundary is when two ocean plates come together. So we get two oceanic plates come together, and there's no choice. They're not going to both push up, so one is eventually going to get pushed under the other one. Whatever one's, thinner usually goes under. And as a result, that same friction that causes those two plates to rub together, way down deep, the magma kind of bubbles up, and then you get volcanoes being formed. And eventually those volcanoes will spew enough magma that they'll actually break through the surface of the ocean and turn into islands. So we have two plates coming together. We end up with a trench. We also call it a subduction zone, where one plate subducts under the other one. And as a result, we end up with something called a volcanic island arc. So because the two plates are coming together, massive amounts of pressure and temperature melt the plates as they go under one another. The magma bubbles up through the surface, and we end up with volcanoes in a chain, typically forming in an arc. This happens underneath the ocean until millions of years elapse, and then eventually the islands will break through the ocean's surface and become actual islands. So places like Japan, Indonesia, the Aleutian Islands of Alaska are all examples of oceanic plate convergence. So I'm just going to go back to our map again. Up in Alaska, the Aleutian Islands. Does anyone watch? There's a couple shows on Discovery Channel. Deadliest Catch. They are based out of the Aleutian Islands. Does anyone watch Deadliest Catch? It's a pretty good show. Sometimes. Kyla, do you remember the name of the city that they're based out of? It's not Haines. Does anyone remember the name of the city in Deadliest Catch? They're actually on one of the islands out here on kind of this panhandle. You get this big arc. Nobody remembers the name? Surely somebody remembers the name. No one. You guys don't get out much, do you? All right, another example. Indonesia is kind of right next to my ear. I've lost my cursor again. Fantastic. So Indonesia, just north of Australia, is another great example of these volcanic island arcs. Japan is also a good example where we have the Philippine plate. There's where I'm talking. So down at the bottom of this image, you can see Indonesia down there, and then at the top we have Japan, where we have two oceanic plates converging. There we go. So those are oceanic convergences. One plate goes under, we get magma formed, the magma breaks through the surface eventually, creates an island. All right, convergent boundaries. First one we talked about was oceanic continental. The second one we talked about was oceanic. The third one we're going to talk about is continental. So you get two really thick plates and they bump into each other. Now because these two plates are so thick, they find it really hard for one to go under the other. So what do? They just kind of run into each other and get pushed up. So we don't get volcanoes because we have these two really thick, fluffy plates, and they run into each other, and they're not going to subduct under one another. They just get pushed into each other and just kind of gets pushed up. So this is where we get the world's largest mountain range, our highest, I should say, above sea level. We end up with the Himalayas. Mount Everest is an example of continental plates coming together. Because we don't have plates going under each other, you don't end up with volcanoes, but because these are two massive continental plates, really thick, running into each other, you get a lot of earthquakes. So places in like through Pakistan, through India, Nepal, you get massive earthquakes. And there was one in Nepal, Mount Everest, I believe it was 2 years ago. There was a massive earthquake, and it actually caused a bunch of earthquakes at Mount Everest, and a bunch of avalanches happened as a result. And I forget how many people died. There was over 10 people that got killed in avalanches because there was a large earthquake at Mount Everest. So they stopped climbing for, I believe they banned climbing Mount Everest for a year, and then they started again this year. So there you go. Those are the three options when you have two plates coming together. You either have a continental and an oceanic plate, two oceanic plates, or two continental plates. Those are the only three options that there are. Let's look at a map, see if we can find an example of two continental plates colliding. If you have a half-decent sense of geography, you should be able to find where Mount Everest is, hopefully. So, I've lost my cursor again. There it is. All right, so we see here we have the, let's see if I can keep my cursor if I go into presentation mode. You can see we have the Indian plate being pushed. We have the convergent symbols, these triangles, being pushed into the Eurasian plate, and we end up with the Himalayas through Nepal, Tibet area, northern India, Pakistan. These are the youngest mountain range, and because they're the youngest, they're the tallest. They haven't had time to weather down. They're very young, very tall. This also happens in Europe a bit. You can get a little bit of a sense of what it looks like in Europe over here, where you have sort of continental plates coming together, and you get the Alps through Europe as a result as well. So there you go. That is what happens when two continental plates come together. So far we've talked about plates coming together, we've talked about plates moving apart, and then the other option is plates slide past each other. And when plates slide past each other, we call it a transform boundary. And transform boundaries are usually found near ocean ridges. Sometimes they occur at the edges of continents. And the most famous one from our area, and probably the most famous transform boundary in the world, is in California. It's called the San Andreas Fault. Because the rock is getting slid past each other, there's nothing coming together, so you don't get any volcanoes forming because there's no friction, subduction causing magma to form or anything like that. So because the plates are just sliding past one another, you get a lot of earthquakes where the plates will lock. You have these massive plates, they want to keep moving, but the plates will get stuck. And then every once in a while, they'll get stuck and then they'll slip. And that's what causes an earthquake. And you get very shallow earthquakes, so very close to the surface, where the plates are moving past each other. They get stuck for, 1,000 years, and then they'll slip again. And I believe the last big earthquake in LA was like 94 or something like that, before you guys were born. It just so happens that the San Andreas Fault runs essentially right under the city of Los Angeles, which is a pretty big deal because there's a few million people that live there, and they are very prone to earthquakes. So this is an actual picture of the San Andreas Fault in California. You can see that there's a clear, very, very clear fault line down the middle where these two plates are running past each other. So the plate on the left would be going down, the plate on the right would be going up, I think. They're going different directions, which is a bit of a problem, especially if you live on or near that line where they're sliding past one another. Pressure builds, they slip, you get earthquakes. No volcanoes, but just earthquakes. So generally speaking, if you're going to have an earthquake, it's going to be at a plate boundary. 95% of earthquakes in the world occur at plate boundaries. The Juan de Fuca converging plate boundary west of Vancouver has many earthquakes. We get big ones every 200 to 800 years. So Madison, you'd mentioned this earlier. So we haven't had one for a while. There was a big one up in Alaska in the 60s, I believe. That was a very, very large earthquake. If you watch the news, it's really funny that I watch the news and then every once in a while I'm like, oh, there's an earthquake. And I'm like, perfect. I'm going to teach earthquakes to my class soon. And there was an earthquake. And I've been doing that for like 10 years. And I always thought it was just a coincidence that every time I taught the earthquake section in science that there was an earthquake happening. But there's just really that many earthquakes happening. They happen all the time. Generally speaking, they're quite small. Every once in a while we get a big one. Jonah here today? No. Jonah is in Haiti, which is still recovering from a big earthquake that happened in, I believe it was 2011. They're still suffering as a result. So yeah, earthquakes happen at plate boundaries every once in a while. We looked a little bit at the symbols. The symbols are always generally the same. Two lines next to each other means that the plates are moving apart. If you have the line with the triangles on it, that means the plates are coming together. And if you have lines with like a single line with arrows going opposite directions, that's a transform boundary. So those are the three boundaries we can get: convergent, divergent, and transform. They always look the same. Some maps will have, arrows showing the direction the plates are moving and what have you. Does anybody have any questions on plate interactions, plate boundaries? We're going to look a little bit about plate boundaries here after we'll take a little break, maybe 10 minutes or so. Nobody has any questions? Plate boundaries. The three types: convergent, divergent. So convergent, divergent, transform. The things that kind of get a little bit tricky is that when we talk about transform, you just got plates sliding past each other. That's it. Nothing really special happening other than earthquakes. When we talk about plates coming together, you can have a thick plate and a thin plate, and the thin plate goes under. You can have two really thin plates and one will go under, or you can have two really thick plates and they just kind of mash into one another. So when we talk about convergent boundaries, there's actually three types. When we talk about divergent boundaries, there's two types. It can happen on land or it can happen under the water. And so when we say there's three types of plate interactions, it gets a little bit more complex than that. All right, nobody has any questions? Put up a timer for 10 minutes. We'll take a break, grab a coffee, grab a drink, grab whatever, and then we will come back and we'll talk about earthquakes and volcanoes, and then we'll actually probably do our activity on Tuesday's class. Probably won't have time to do it today. So take a break. See you back in 10. Thanks. Hi guys, welcome back. We can get some green check marks up. Let me know you're still there. Got some slow internet loading here. All right, thanks. So section 10.2 is a bit of a long one, and I find earthquakes and volcanoes really interesting, so I like to spend a little bit more time on it, and kind of breaks apart section 10.2 because it is a lot of information. So we'll talk about some earthquakes and volcanoes. Does anybody know where this volcano is? Anyone recognize this one? Kind of a famous one. Yeah, Kaylin, you got it. This is Mount Fuji in Japan. So remember Japan, we have two oceanic plates coming together. One goes under the other one. Magma rises up, becomes lava, and it has created the actual chain of islands that is Mount Fuji and the rest of Japan. So we'll talk about volcanoes and a little bit of earthquakes. And then next class we'll go through an activity together. We might do today. I don't know. We'll see. We don't have a ton of stuff to get through over the next few days, so maybe we'll just take our time. So we'll talk about earthquakes for a bit, and then maybe we'll just call it a day after the earthquake stuff. We'll talk about volcanoes next day. That'll probably be a good plan. So Madison alluded to it a little bit earlier. We're due for an earthquake in the Vancouver area. We haven't had a big one for a long time, and we haven't had a lot of little ones. So earthquakes are very difficult to predict. It's not something that we can say, okay, an earthquake happens at 12 o'clock every 100 years to the day, and you just wait for it to happen, you get ready, and your earthquake happens, and then you kind of go on with your life. That's not how earthquakes work. They happen whenever they want. They don't really care about us or whatever we may have built near them. We understand why they happen. We know that the plates are either subducting or getting slid past each other, and they get stuck, and the energy builds and builds and builds and builds and builds, and then they slip really quickly, and that's what an earthquake is. So it's either a transform slip going past each other, or one getting subducted under the other one gets stuck, and then it goes really quickly. It happens underground. It happens over very, very long periods of time. And we have kind of two words to describe where an earthquake happens. We have the focus and the epicenter. So the focus is the actual spot where the earthquake happens. And the focus can be hundreds and hundreds of kilometers underground, or it can be right at the surface. The epicenter is kind of what we care about a little bit more. So the epicenter is the place on Earth's surface directly above where the focus was. So this is an example of kind of a subduction type scenario where you have a fault, and the plates are kind of moving, and this plate slips down off this other one. The earthquake, the buildup of energy actually occurred here. This is where the plate slipped. We call that the focus. We go directly above the focus to the surface of the Earth. It's the epicenter. So even though we see the fault line way over here, the earthquake can literally happen hundreds of kilometers away from where the actual visible fault is. So we kind of know what happens during earthquakes. We know we build buildings in at least North America to specific standards to withstand certain levels of earthquakes. All of the sort of public buildings and schools and things have been earthquake proofed. I remember it was not long ago, I was teaching at KSS, and there was kind of the science storage room had all these racks with sciencey stuff, weights and optics tables and all sorts of other stuff. And these people came in, and there was literally their job to drill holes in the wall and mount all of these racks right to the wall. They went through, and there's all the grad pictures in the halls of KSS. They started drilling little supports so the pictures wouldn't fall off the walls in an earthquake and things like that. I was just reading another news story the other day about the Vancouver School District is due for seismic upgrades, and it's going to cost millions of dollars to kind of fix all of their schools. The province is, given some money towards that and things like that. So earthquakes can happen at various depths depending on the plates. If you have transform plates, usually earthquakes happen very shallow, very close to the surface. If you have subduction, the actual earthquakes can happen way down hundreds of kilometers underground. Very shallow earthquakes, the ones that are very close to the surface, tend to cause more damage because they're very close to the surface. The energy gets released at the sort of surface. If you get a very, very deep earthquake, the energy has to travel through rock and kind of gets dissipated as it travels up towards the surface. Transform plate boundaries cause shallow earthquakes. Subduction zones produce deep and shallow. And we looked at tsunamis not long ago. That was a result of an earthquake off the coast of Japan. So remember, Japan, we have a subduction zone. We have two oceanic plates. What happened to Japan was the oceanic plate that was getting subducted, it started to go under and it got stuck. And eventually, the place where Japan was, it slid and it literally moved on Earth. It moved like 2 meters. Just instantly, almost 3 meters, Japan moved kind of closer to us by 3 meters in the fraction of a second. Because that shift happened, a big wall of water was created and washed inland, killed thousands of people. Very devastating effects. Some people call tsunamis tidal waves, but they're not really the same thing. There you go. So here's a map of all the earthquakes in the world from 2002 to 2011. So we're talking almost 10 years. And the red dots are shallow earthquakes. So the red dots are earthquakes that happen in the first 33 kilometers of the crust and upper mantle. A yellow dot's a little bit deeper. That's up to 100 kilometers deep, so 33 to 100. I don't know if you can see the legend very well. The green dots are up to 400 kilometers below the surface, and the blue dots are 700 kilometers below the surface. So once you start getting down 700 kilometers, it's fairly liquid down there in terms of the mantle. But remember, if you have a plate going under, that plate is solid rock. It's melting, but it's still pretty solid, and it's sliding past that other plate. We get these earthquakes. So really interesting stuff here. Up in our area, we end up with a lot of red dots, so very shallow earthquakes. There's a few yellow dots getting into the deeper ones, but we don't get the really deep earthquakes in our neck of the woods. We look at somewhere like the Andes down in South America, you end up with a really, really thin oceanic plate getting subducted under a really thick continental plate, and you get these kind of shallow earthquakes right on the coast. And then as you go further inland, you end up getting deeper and deeper earthquakes. So it kind of makes sense that the shallow earthquakes happen right where the two plates meet. If you have subduction happening, right where the plates meet, you get these shallow ones. The further the plate goes under, so now the really deep earthquakes are way over here. If I talk about the epicenter, so the place directly above, if I went straight up, they're not where the plates met over here. The really deep earthquakes are way inland. So if we look at the map, you'll notice that the deep earthquakes aren't at the edge where the two plates touch, kind of at our surface. The deep earthquakes are literally thousands of kilometers inland because they're hundreds of kilometers underground. Another example is off the coast, kind of over towards New Zealand. You see all these blue dots because we have two oceanic plates getting subducted under one another, and you end up with really, really deep earthquakes. Even though the plates are actually meeting over on this edge here. So this is where the plates meet. You get these shallow earthquakes, then you get a little further, they get deeper, deeper, and you get the deepest earthquakes. So there you go. There's earthquakes all over the world. We live in the Ring of Fire on the sort of Pacific coast here. The Pacific Plate has all of these boundaries around it, and right in the middle we have Hawaii, which experiences some earthquakes, and we'll talk about why that is here in a second. So this is kind of a cross-sectional view of how these earthquakes happen. The surface, you get those red dots. They're right where the two plates touch. As you get further down, you get the immense pressures building. You get into the green dots, which happen at a lower level. So we're talking below crust level. And then we get the blue dots, which are happening way, way down. So we know that the plates are still plates and solid hundreds of kilometers under the surface, up to like 500, 600, 700 kilometers under. That's how far the plates extend down into the mantle, because we know that there's earthquakes happening down there. If there was no earthquakes down there, we would assume that we don't see any earthquakes deeper than about 600, 700 kilometers, because the plate is melted by the time it gets that far down, and then it continues the cycle. All right, the Ring of Fire. Here we go. Any Johnny Cash fans out there? No, I won't sing for you. So the Pacific Plate has all of these plate boundaries all around the outside of it. It's called the Ring of Fire because it's the most volcanically active places on Earth. I've actually been to an active volcano in Costa Rica. I think, Jenna, have you been to Costa Rica? Jenna, your family's been everywhere. Anybody been to an active volcano before? Jenna, did you go to volcanoes when you were in Costa Rica? There's lots and lots and lots of volcanoes in Costa Rica. The one I went to is called Volcano Arenal, and you can't get too close to it because it's active, and it's constantly spewing flaming hot boulders and lava and stuff, and it's really cool. At night you can look up and it glows and there's like clouds above it, and it's really quite a cool experience. There's lots of water and pools near the volcano where you can go just sit in these kind of like natural hot springs because the so much heat underneath that volcano. Jenna's the only person in class who's been to an active volcano. Interesting, very interesting. I recommend it. Go visit a volcano one day. It's good fun. I want to talk a little bit about Hawaii. So we have this Pacific Plate, and we're right in the middle of this Pacific Plate. Has anyone been to Hawaii before? That's a pretty popular destination. Of course, Jenna has. She's been everywhere. Leeds, Costin, nice. So some of us have been to Hawaii. Hawaii, if you've been to the kind of the big island, I think it's actually called Hawaii. It actually has lava kind of pouring out into the ocean almost consistently all the time. So that's pretty cool. But we've talked about it. Volcanoes usually happen at the edges of plates, right? So why is there a volcano in the middle of a plate? It doesn't make any sense as to why there would be a volcano in the middle of a plate. So how can we describe what's going on there? Any ideas? All the other volcanoes are happening at the edges of plates where we have, either plates moving apart, plates coming together. This is quite literally almost the exact middle of this Pacific Plate. We have this Hawaiian island chain just kind of hanging out there and a bunch of volcanoes. Is the plate cracked? It kind of is almost, Jenna. It's kind of the same idea as what we talked about over in Africa. In Africa, there's this really strong convection current under this edge of the African plate, and we get all these volcanoes forming and a rift valley forming and soon to be an ocean. The hot spot under Hawaii is a very, very strong convection current that exists in the middle of this plate, but it's not strong enough to create a rift valley. It's just strong enough to kind of break through in a few spots. So the plate kind of gets cracked because we get things pushing through so much. So I'm gonna jump into Google Earth, maybe? Of course, I don't have Google Earth installed on this computer because it's a new computer. Let's see if I can do a web app type deal of Google Earth. Just give me a second. My awesome computer to load this. I I don't want to download it. Can I just do a web-based version? Devastating. All right, maybe we're not going to look at Google Earth. Maybe I can just go to Google Maps. That might be a good substitute. There's Kelowna. Let's look at an Earth view. I don't know if this is going to show what I'm hoping to show. By Kelowna. There we go. All right. Here is Midway Atoll. That's not what I'm looking for. There's the Aleutian Islands, Alaska. This is a great, I should have done this before. This is way better. Here we go. So I'm not getting the same thing on my, there we go. So this shows you the Gulf of Alaska. Got some crazy stuff happening on my monitor. Here's the Gulf of Alaska, here's Alaska. These are the Aleutian Islands. So we have this Pacific plate. These are all volcanoes along here where these two plates come together. And when you look at it from space, it's really obvious to see, well, this is, composite images, but it's really obvious to see that you have this plate being subducted under this thicker plate, and you get all these islands being formed as a result. So that's a really, really cool way to look at things. All right, let's see if we can find Hawaii. The Midway Atoll. There's Hawaii right there. Okay, so I'm just going to zoom out a little bit further if I can. Beautiful. Just wait for my screen to load. Hawaii. Oh, now I get weather. Not sure I want weather. There we go. All right, so here's Hawaii. Don't give me weather again. What you'll notice about Hawaii is that there's a big island down here. This is quite literally the big island, Hawaii. And then you get like, I don't know all the names, but this one's Oahu over here, and then you get Maui over here. And then there's this kind of chain of kind of underwater islands that just continues beyond Hawaii. So if we look at one side of Hawaii, there's a bunch of islands, and we look at another side of Hawaii, and there's no islands. So over in the other direction. There we go. So there's nothing over here, but there's this long string going the other way. And I will tell you one other thing. The only active volcanoes in Hawaii are these guys on the Big Island. So what's going on here? Basically, this big Pacific plate, it's there. And right in the middle of the Pacific plate there's a hot spot. And it wants to push magma through, and it finds a weakness, and it does, and you get a volcano. But that plate is constantly moving. So the hot spot stays where it is, but the plate is constantly moving over top of it. And what happens is that hot spot's been there for millions of years, pushing up, breaking through. And because that plate is constantly moving, the very leading edge of Hawaii, you can actually see off the coast of Hawaii, there's a new island forming just in the ocean. Over here, you're going to eventually end up with a new Hawaiian island in another few 100,000 years. But that magma's been pushing through that surface for a long, long time. We follow Hawaii this way, you get this big long tail. We've got super slow, laggy connection today. You get this big long tail of islands going back thousands and thousands and thousands and thousands and thousands and thousands of years. So as Hawaii, this hotspot pushes up, it pushes up, we get magma flowing through, we get an island, and the plate keeps moving. So I'll ask you a question, maybe some of you can think about it if you process things quickly in your brains. Why is the newest island the largest, and why is the oldest island the smallest? Why would the newest island be the biggest and the old islands? Like the old islands of Hawaii don't even break through the surface anymore. So why is that? Why do they not break through the surface anymore? The water levels we'll assume like they have changed a bit, but why? We'll assume that they're the same as they used to be. It's not significant enough to cause what I'm trying to describe here. So in the image you can see up here the we can see the plate is moving and the plate's kind of cruising along this way. That hot spot stays here. So these islands get smaller and smaller as you go, and then this is a seamount, so this one doesn't even break through the surface anymore. Any other guesses? We have water level change, possibly. Not the one I'm thinking of. Why are the older islands smaller? What happens, has anyone been to a beach before? Has anyone been to a beach? Yeah, a couple of us. A few of you got out, visited a beach. What's a good quality you look for in a good beach? Something you like about a beach? Sand, soft sand, sand. Yeah, you like that white, nice sand. Water helps. All right, let's put these two ideas together. Sand, water. How did the sand get there? It has something to do with water. We like the sand, we like the water. Together, yes, the water erodes the rocks into sand. So now imagine this. You are an island. You are the new island of Hawaii. You're the Hawaiian island called Hawaii. You have magma, lava flows everywhere. But you go to some places on the big island of Hawaii and there's sand beaches. The water has been crashing on shore for, thousands of years, and it wears those rocks down into sand. Now imagine you're an island that's 1 million years old. Pardon me. 1 million years old. That water's been eroding you for 1 million years. You're in the middle of an ocean. You're completely surrounded by water and storms, and it's a free-for-all out there. So because the old islands have existed for so long, they've literally just been hammered by waves for millions of years. They get smaller and smaller and smaller and smaller until they no longer break through the surface anymore. So if we look at the image down below here, the time frames are in MA, which is millions of years. So we can see that the current Hawaiian islands, we can kind of see the hot spot underneath the islands. My cursor would show it, but it's not going to. The hot spot's there. This is about 700,000 years old, the newest Hawaiian island. Maui is about 1.3 million years old. Oahu is about 3.4 million. As you go further back, they get smaller and smaller and smaller until they're gone. Kauai, 4.9 million years old. Oh, my cursor's not the same spot. So as you get further away from the hot spot, it literally takes millions of years for that plate to kind of move that far. And in those millions of years, the plates, or the islands that are formed, get eroded by wind and water and rain. And the rain washes the rocks into the ocean, and you get sand on the beaches because the rocks are constantly being bombarded. So the smallest islands are always the oldest because they've been eroded over millions of years. So you get this hot spot, and it breaks its way through. So in about another million years, the big island of Hawaii will actually be a few hundred kilometers over, and there'll be a new island formed. And that new island will be essentially bigger, or it might get bigger than Hawaii. The other hot spot I want to talk about is Yellowstone. So the image on the color sort of image of North America here is a little bit deceiving, but right under North America, down not too far away from us actually, Yellowstone is a park. Has anyone been to Yellowstone Park before? Down in corner of Montana, Wyoming, Idaho. Come on, please tell me somebody's been to Yellowstone. It's probably one of the coolest places in the United States in terms of just animals and geography. Your dad went there when he was a kid. It's like a day's drive from Kelowna. I mean, a full day, maybe a little bit longer. Yeah, you guys got to go to Yellowstone one day. So anyways, the picture on the left shows if North America was kind of like perfect and flat. And what's happening is underneath Yellowstone National Park right now, there's an enormous convection current happening. But it's happening under a thick continental crust. So if we talk about Hawaii, the crust is so thin that the lava can break through and it just, it relieves the pressure, no big deal. But if we go to this thick continental crust, we actually have a hotspot underneath the North American plate, and it's trying to break through, but it can't because the crust is so thick. So this red is showing how many meters this area is actually being pushed up because of the hotspot underneath it. Now, it doesn't really seem like a lot, like 10 meters, no big deal, but it's supposed to be flat, and there's literally a plume of magma pushing it up, and it's actually about 10 meters higher than it actually should be, which is significant. And that magma is going to eventually try to break through the surface. So Yellowstone's really cool because there's geysers and these like hot pools of mud. And have you guys heard of maybe Old Faithful before? It's a geyser that erupts every 7 minutes exactly. It's pretty cool. Yellowstone Lake is actually a pretty cool place too. It has some really cool features where there's kind of like bubbles and stuff under it because it's very active. So we have a giant caldera, which is basically a volcano just waiting to erupt under Yellowstone. You guys watch movies. What was the movie that had the super volcano under Yellowstone? Does anybody remember that one? I think it was it might have been 2012. Was that the name of the movie, 2012? The Day After Tomorrow. Was it The Day After Tomorrow or was it 2012? Anyways, there's a movie that actually has this hotspot portrayed in it. I'm going to show you one. Yeah, it was 2012. 2012 for sure. One other thing that I found really cool. I've been to Yellowstone before, and I hiked around and did some sightseeing and stuff. It was pretty cool. There's a place in Idaho, which I've also been, right here. So this is a picture from space. This is not a picture from space. This is just blue ocean because the computer is taking a second to load. And that's okay, so we have time. All right, so we're going to zoom in here in a second on Idaho. Beautiful. Here is Idaho. Now, imagine we're in space and we're looking down, and there's this place called Craters of the Moon National Monument and Preserve. There's also some other stuff that you can see. Why is the land so brown? And then you get into this kind of area here and it gets so dark. Let's zoom in a little bit. This may take a while longer than expected. All right. What does that look like to you guys? All of that, well, I'll give you guys a second to see what I'm seeing. What does all this stuff look like? If you were to guess and say, there's a bunch of really black rock or black stuff in the middle of the brownness. What is it? It's not coal. What other rock do we know that's quite dark and black? Obsidian basalt. You guys are really good at your rock types. I'm going to go even simpler than that. All of this stuff, it's volcanic. It's magma. If you look and think of magma, it comes out of the ground and it hardens and it's black. It's very dark. So this whole area is full of, I wonder if I get close enough I can get some pictures, is full of magma that broke through the surface. And, you can see it, all these magma flows in the middle of this kind of plainsy desert type area. And this is the same hotspot that's currently under Yellowstone National Park. So this is called Craters of the Moon. There's a bunch of magma flows all in this area. And the hotspot that's currently under Yellowstone, because the Pacific Plate is kind of moving, it's floating on the asthenosphere, it's moving over, the Yellowstone supervolcano caldera used to be over here. So in this image you can see Yellowstone. You can't see it. It'll load in a second. On the top right corner, up here, we've got Yellowstone. And then down over here we have Craters of the Moon National Park. So a few thousand years ago, the hot spot was way over here. And it actually broke through the surface. And all of these black things are lava flows at Craters of the Moon National Park. Now that hotspot is currently under Yellowstone. And it is a bit of a big deal because it's a supervolcano just waiting to erupt under Yellowstone National Park, but the magma can't find its way through yet because it's a little bit thicker over there. So I'll just bring up a few images of Craters of the Moon National Park, and then we'll call it a day. So this is what the Craters of the Moon National Park looks like. It's a really, really cool place if you ever get an opportunity to visit. So there's all of these like lava flows in the middle of nowhere. There's no sort of volcanoes there, but this super volcano that's underneath North America is pushing through. Thousands of years ago, hundreds of thousands of years ago, it broke through. And you can see all these really cool lava formations all over the place, and just lava for long, long distances. It's quite amazing to go see it. So this is currently under Yellowstone National Park, but it can't break through. So this is a problem, and it's expected that Yellowstone will erupt one day. We hope that it erupts slowly like it did underneath Idaho, but it is possible that it could just explode and blow up because the volcanoes in this sort of area have a bad habit of exploding. That's a lot of information for now. I think we'll just probably call her a day there. Does anybody have any questions? Next day we'll continue on, and we'll need to drag that. Next day we'll continue on. We'll finish talking about earthquakes and volcanoes. We'll talk about seismic waves, and we'll do a bit of an activity with there's an online simulation. Just out of curiosity, how many of you have Macintosh computers, Mac computers at home, and only a Mac computer? So only have access to a Mac computer at home. There's a few of you. One or two. All right. So there's a Java activity I wanted to do, but you guys won't have access to it. So I'll pick the other activity that doesn't use Java, and we can go from there, just so everybody's able to participate. So we just need to talk about seismic waves, and that's essentially it for this unit 10. So that's kind of it. We did the meat of everything today. Where are we at? Should have units 1, 2, and 3 done for sure. Interim reports will go out on Monday. Marking will be cut off Friday. And it's important that you get in everything if you want marks for things. If you don't, then don't submit anything, I guess. I don't know. It'd be great if I could give you a mark. Just if you have something done, just submit it. I'll give you some credit, obviously, and it might be enough to get you guys to a pass. So there you go. I'll leave you there. Hopefully everyone has a great afternoon. If you're interested in coming to H2O tomorrow, Mr. Fender, and I think there's about 20 so people signed up, H2O tomorrow. You can see it on the schedule. And if not, I'll see you guys on Tuesday in class. I hope you guys have a great weekend, and we'll see you then. Thanks.